The EU, like most of the world, needs to reduce its dependence on oil and gas. By 2020, it wants 10% of energy used in the transport sector to come from renewable sources. In order to meet this target, manufacturers have been developing cars which run on alternative fuels such as electricity and biofuels. Biofuels are byproducts of industrial waste, for example gases, alcohols, organic compounds and oils. They originally come from vegetable or animal matter. There are two main types of so-called first-generation biofuels. Biodiesels, made for example from rapeseed, sunflower or soybean oil, and bioethanol, produced from plants such as sugar beet, sugar cane, cereal crops, wheat or maize, and blended with diesel. The advantage of this alternative energy source, it helps reduce greenhouse gas emissions. The drawback, its production can have damaging environmental consequences, such as water pollution, deforestation, and change of land use. For example, farmland traditionally used to grow crops for food supply is often being diverted for biofuels production. This was one of the triggers of the 2007-2008 world food price crisis. To counter the problem, researchers are developing ways of replacing current biofuel production methods with so-called second-generation processes, using what is known as biomass, organic waste, wood chippings, straw and hay. This reduces the impact on the food chain but is a more complicated process requiring sophisticated technology. The thermochemical route involves producing combustible gas or liquids such as diesel or jet fuel. The biochemical method typically uses the cellulose found in plants to ferment ethanol.
In 2012, UPM started building a hydrotreatment biorefinery in Lappeenranta, Finland. Once ready in summer 2014, it will have a yearly production capacity of 100,000 tons of high-quality renewable diesel, UPM Bioverno, for road transport. UPM Bioverno diesel is produced from crude tall oil, a residue of pulp process. This renewable raw material originates from sustainably managed forests. The whole process results in significant reductions in greenhouse gas emissions. UPM's new biorefinery takes shape in Lappeenranta. To a great extent, this is thanks to our own research and development team in the UPM Research Center, part of our innovation in wood-based advanced biofuels.
Welcome to UPM Research Center. The first steps for UPM biofuels, namely the idea of producing renewable diesel from crude tall oil, was born here. It has been developed further by our researchers and key partners.
UPM plans to become a major player in advanced biofuels, the front runner in quality, usability and sustainability of biofuels.
UPM Biofuels aims to grow by converting solid biomass into advanced biofuels. A lot of effort is put into research and technology development. In the long term, we are looking for possibilities to expand with new raw materials and emerging technologies. We have a lot of things going on here in Lappeenranta. Our focus is clear. We concentrate on new generation fuels based on residues.
The thermochemical conversion process uses heat to break down biomass into intermediates, such as gas or bio-oil, which can be upgraded into fuel and other products. One type of thermochemical conversion process is pyrolysis, a method that uses heat to decompose biomass in the absence of oxygen. Here's one example of a pyrolysis conversion process. Wood material, such as forest residue, is a common feedstock for the pyrolysis process. For best results, feedstock particles are less than 2 millimeters in size and have less than 10% moisture content by weight. The process of pyrolysis heats the biomass at moderate temperatures in the absence of oxygen. This produces vapors that are condensed into liquid bio-oil. Char is also produced during the pyrolysis process. Cleanup and stabilization of the bio-oil make it more suitable for storage, downstream processing, and end use. Cleanup can consist of filtering out particulates and ash before the bio-oil is condensed into a liquid. Stabilization typically involves mild hydrotreating, a process that uses hydrogen to remove contaminants such as sulfur, nitrogen, or in the case of bio-oils, oxygen. Hydrotreating occurs with high hydrogen pressures in the presence of catalysts. Oxygen is eliminated mostly as water along with some carbon dioxide. Other processes to remove oxygen are also being examined. Eliminating oxygen creates a less reactive bio-oil with lower acidity. The less reactive bio-oil may be stored longer and is more suitable for use as a fuel oil. The less acidic bio-oil may be more readily accepted into current infrastructure by achieving chemical compatibility with infrastructure materials such as pipes, reactors, and tanks. Mild hydrotreating is usually followed by more severe hydrotreating, which is required for the bio-oil to be suitable for use in a conventional petroleum refinery at several insertion points. Then, using technologies employed by existing refineries today, the bio-oil goes through a hydrocracking process, which tailors the molecule sizes to be in the desired range for gasoline, diesel, or jet fuel. The Department of Energy is supporting development of innovative technologies that result in higher quality bio-oil that lowers subsequent upgrading costs, allows for longer storage, and improves commercial viability. Advancing these technologies will help bring clean, renewable transportation fuels to the marketplace that can be used in place of petroleum.